First, about parametric design. So last time, in the last two lectures, basically, we saw how to create parts. But one of the important things about parts, and especially standard parts, the parts that you find off the shelf from hardware stores and here and there, is that all of the dimensions in a part, they are not typically independent from each other, okay? For many basic parts like bolts and nuts, gears, bearings, and so on and so forth, there are some fundamental dimensions, we call them parameters, that everything else is basically a function of them. For example, in a bolt, nut, and washer system, as you can see, the major diameter of the bolt, okay, this diameter D is the big parameter, the major parameter. So if the diameter major is D, then the size of the head of the bolt is typically not arbitrary. It is related to D, it's 3/4 of D, right? Or the size of the washer is 1D, the thickness. The thickness of the thickness of the washer is 15% of D. Typically, the length of the thread is like 2D, and the size of the head from corner to corner is 2D. The diameter of the washer is 2D plus 4 mils. Okay, so you see that these are not completely independent. Another example, as I said, is gear. So in gear, there are some fundamental parameters. One of them is called gear modulus, or the reciprocal of that, we call it diametral pitch. So in a gear, actually, as you can see in this picture, there are so many different circles, okay? So we do not have one circle defined, and so not one diameter. So there is a circle that is passing through the tip of the teeth, okay? We call it outside diameter, or the actual technical term is called addendum. So it's called addendum circle, and then there is one that goes through the roots of the teeth. We call it didendum circle. There is one that is somewhere in between, not exactly. It's called the pit circle. This pit circle is such that when two gears are meshed like this and the teeth are in contact and moving together, the pitch circles of the two gears are tangent to each other, okay? The only two circles that touch each other and not intersect or not completely are separate are the pitch circles, because the didendum circles never touch each other. There is also another circle, it's called base circle, we'll talk about that later, and that base circle also never touch. It's very close to the didendum circle. The pit circles are tangent to each other, and then the addendum circles will basically intersect at 2 points. So basically, if you replace two gears with two pulleys or two discs, okay, that are in contact with each other and they move each other just by friction, then the diameters of those two pulleys are what? Equal to the pitch diameter of these two gears, right? So again, so here I have these two gears, and again, if instead of these two gears, I replace them by two discs that are in contact just by friction, like this, then the diameters of these two circles, this one, or radius if you want to call it, doesn't matter. So this diameter and then this diameter, these are equal to the pitch diameter of these two guys, okay? So if you call this cap D, and this is like D1 and D2, so this is D1, and then this is what? D2, the diameter of the pitch circle. Now, here, one of the important parameters, as I say, we call it the gear modulus. So one of the important parameters, M, and this M is defined to be the diameter of the pitch circle divided by the number of teeth, N, on the gear. And this is an important parameter. Why? When two gears are meshed together and they need to work together, the modules of the two gears have to be equal. So here, if this gear has, let's say, N2 teeth, and this one has N1 teeth, then for these two gears to work together, D1 over N1 should be equal to what? D2 over N2, okay? Or the two moduli actually here have to be the same. Otherwise, they don't work. And probably you experience that in your, let's say, or you will experience that in your EGR 101 course, where you wanted to basically put gears together and, let's say, reduce the RPM or do something with it, transfer the rotational power. You found that not all two gears in the Lego kit will mesh together, right? Only those who have the same modulus. So let's say here, this top gear has what? As far as I can see, 3, 6, 11 teeth. So this guy has 11 apparently. And this one, you just count half of it. That's 5, 6, 7, 8, 9. That has 18. Okay. So then from here, you can also say that N2 over N1 is the same as D2 over D1. And since here N2 over N1 is 11 over 18, so the ratio of the diameters, or the size of its two gears, is also equal to 11 over 18. So clearly you see the bigger gear has more teeth. But how much this one is bigger? This is 18 over 11 times the other one. Okay, so for example, if the other one has 22 instead of 18, so it had 2 times more teeth, then the diameter of that should also be 2 times bigger than the other one. So the ratio stays the same. Okay, so this is one of the very, very important parameters in a gear. We call it gear modulus. That's the most important one. In some systems, especially the British system, instead of gear modulus, they use reciprocal of that, and they call it diametral pitch. Okay. So this diametral pitch is 1 over m, and that is the number of teeth divided by the diameter of the pitch circle. So that's another way that some standards define this parameter. So that's one of the parameters. The other important parameter you have is called phi, or pressure angle. And what is pressure angle? So if we go back to this picture, so when the two teeth are in contact with each other, so here, this area, if you see the two teeth are in contact, the common normal to the profiles, the common normal is this line here, which we call it basically line of action, this line. So this is the line along which the force is exchanged between the two teeth, or between the two gears. Okay, so this line of action is the line where the force is exchanged. Now the angle between this line of action and this line here, which is perpendicular to what? The line that connects center to center. So this line, vertical one here, connects center to center. Perpendicular to that is horizontal in this case. The angle between this normal to the center to center, this line, and the line of action, this angle is called what? Pressure angle. Okay, so the forces here if I show the force exerted on the small gear by the big gear, the force F has an angle like this, phi. Okay, and so this force actually has two components. If you decompose the force, this horizontal one is F cosine of phi, and the vertical one is F sine of phi. And it's this cosine of phi that creates moments about the centers and make them rotate. The F sine is just pushing the gears to their bearings. Okay, it does not create any moment, only this one does. And of course, the bigger it is, the bigger the moment or the torque on the gears, which is a desired property. And clearly, if F is constant, you want cosine of phi to be as big as possible or phi to be as small as possible. So when phi goes up, cosine of phi goes down. Therefore, F cosine of phi goes down, and therefore the torque, which is basically this force, right? The torque is that force, F cosine phi, times the diameter, which in this case we call it d2 over 2 or d1 over 2. This one is going to go down, so the torque goes down. Okay, so having large pressure angle is not a desired property. It increases the pressure on the bearings when you make it bigger, but it reduces the torque, so we don't want that. Okay, but anyways, based on that phi, if you so how do we determine different things in a gear? Again, I don't want to make this class like machine design class, because you need to learn about gears in machine design, but as far as I know, not all of you will take machine design, so I'm just trying to tell you a little bit about gears. So the important parameters will be now N and M. If I know N and M clearly from this definition, I can find what? I can find D, right? Because D is going to be what? M times N. So if I give you the number of teeth and the gear modulus, you can find the diameter of the pitch circle, which is one of the important steps. And then when I give you phi, you can find the diameter of this circle called base circle. That's important. And also based on those, I can also find the diameter of the didendum and the addendum, the root and the tip circles too. So important parameters in a gear are these three guys: N, M, and phi. Number of teeth, gear modulus, and pressure angle. Okay, so gear has more than one parameter. But once you know this, everything else, as you can see, will be determined based on that. Okay, so the diameter of the base circle is diameter of the pitch circle times cosine of the pressure angle. Then you can find, for example, the outside diameter or the addendum circle, right? It is going to be N plus 2 over P, where P here is capital P is pi times small p, and small p is basically pi d over n. So this small p, we call it circular pitch, is pi times gear modulus. So circular pitch is pi times gear modulus. Okay, and then if you divide it by that, diametral pitch. So here you see diametral pitch is cap P, diametral pitch is this guy that I mentioned for you. Okay, I call it dP, but this lecture call it P. So diametral pitch P, if I know that, which is reciprocal of gear modulus, 2 divided by that number plus what? The number of teeth, N, will give you what? Diameter of the outside, and then you can find diameter of the inside, and everything else. Okay, so you can find basically everything you want. Addendum, didendum, anything can be found here for you. Okay, extremely important. So these are some of the formulas. So now, how do I implement that when I'm designing some part in SolidWorks? So let's say I'm creating a bolt, okay, and I just make the base of the bolt. I'm not going to make the threads, so I just want to make the base of the bolt. And so if I know D, I also want to make sure that the size of the head is 0.75, and then the corner to corner of the hex head is 2D. right? And then I can also, another parameter in the thread, in the bolt is L, okay? L is the total length of the shaft. So L is another parameter that is independent from D in general. So let's say I have L and D and I want to make the base of the shaft, okay? So how do I do that? So first, I need to create two variables. Okay, we call them global variables, one of them to be L, one of them to be D, and then we're going to use them when we create this bolt. Okay, so how do we do that? So here I'm in SolidWorks and I go to new part. Okay, there we go. And then I will first create two parameters. So I will go, in order to create equations and parameters, you go under Tools, and then go down until you see the sigma symbol here, Equations. You click on this to get your window show up. Then under Global Variables, you find a parameter cap D, then you use a tab to go to the next. And here, do you want to use the functions in SolidWorks to define it, or do you just want to directly type it? I would say let's type it, and I would say, let's say it is 1 inch. So I type in 1 inch, so you have to provide units, okay? Make sure you provide units. And now it is added. Then I also come here and create another one, L, and let's say L is like 4 inches. Okay, so I got my two parameters and I okay that. When I do that, now under my tree, there is a new tab added, a branch added called Equations. And if I expand it, I can see the values of my parameters and I can modify them if I want. I right click here and say Manage Equations. I come back here and then I can click and change the numbers. Okay, so keep that in mind. So now I am going to create the hex head and then the shaft. How? So first I go, let's say on the top plane, create a sketch, use the hexagon, click here, and then basically click the hex head. Now you need to make sure this corner to corner, the dimension is 2 times D. So I bring it out and click one time. Now here in this window, instead of me typing a number, I say this is equal to, and then I can again insert functions or what? Choose my global variables. And I say this is D and then what? Times 2. So 2 times D. And you see D was 25 mil, so this is 50 mil. Right? So just that simple. And you see now this dimension is different than if you just entered it, because now there is a sigma appearing next to it. And that sigma means this dimension is not independent. It is now depending on something else. There is a function for it. Okay, so this is good. Now I get out and I have to extrude it. So when I want to extrude it again, I have to make sure the size of extrusion is 0.75 D. So here, instead of me for the blind typing a number, again I say what? Equals, and then what? D, and then times what? 0.75. And I okay that. Okay, so let's first do the circular cut around it, and then we'll go to the circular shaft. So here, no, apparently it chose a midpoint or something. So let's make sure this point, yeah, is not a midpoint so that we can provide dimension. And here, Again, if you want, you can relate it to D. I don't have the formula for it, so I can just type in a number for now. But these are not even independent too, okay? Everything is depending on something else, mostly. So let's say I made this, and now this is ready to be cut revolved, but I also need another line or something to use for my axis. Okay, so I choose this, then click on the cut revolve, and for axis of revolution I choose the axis I made, and there we go, that's the cut. And I can hide the sketches. So that's the head. Now I go on this surface and draw a circle. Note that the diameter has to be equal to D. Right, so this is equal to D. And then you extrude it and make the length to be equal to L. And there we go. Yes, so now it is parametric. What does that mean? Means if I go and change my parameters, this bolt will be updated based on the new dimensions automatically. So let's say I want it to be a little bigger bolt. So I go to manage equations, and then I change this diameter to be like 2 inches, and I make the length of it to be like 9 inches or so. Yeah, so just pay attention to how it is updated. There we go. Yes, so it is important that we design in a parametric fashion so that if we want to modify anything, we do not have to basically come back and put all the dimensions one more time from scratch. All we need to do when it's parametric is to just go and change parameters and get a different part, basically, which has the same overall configuration but different dimensions. Okay, so this is using basically global variables and referring them to dimensions. I can also show you that you can insert the equations in sketches in a different way. I'll show you that, but I'll show you how to use it in 3D features and how to modify them. So if I go back here to this shaft dimension, so here what I did was I inserted this dimension, right? And then instead of me clicking here and then typing a number, I use equal sign and then use one of the global variables. So that's one way. The other way is this. You just give it a number, anything, just initial number, and then this is how you can insert an equation in another way. Is you click on this dimension one time, just highlight it, or even if you don't highlight it, just first go under tools and click on the equations, or go over there in the tree and say manage equation. And now here you see the equations that I made in the past are already added here, so I can add one more here if I want to. So I check here, then click on this dimension. Each dimension has a name in SolidWorks. So this dimension is called D1 at sketch 7. Why? Because this sketch I'm making is called sketch 7, and that's the first dimension I'm making in it. And then I can say this is equal to what? D. So that does the same thing as last time. Okay, and okay that. And there we go. Right? So you can insert it like that as well, or when you are creating it, just use equal sign and type the formula in that small window. Okay, now In addition to using equations and dimensions in 2D and 3D sketches and features, we can also export our equations all to an external text file. And then if you edit the text file, your SolidWorks dimensions or formulas will be modified accordingly. In other words, your SolidWorks file and that text file are linked together. Okay, so you just need to say link to external file. Okay, so let me show you that. So I'll go here and go to equations, and as you can see, I check this one, says link to an external file, right? Correct. So that's how you link to an external file if it exists. If it doesn't, then first you have to basically create it and link it. So here when I say link to, it says, okay, do you want an existing file? Say no, create one for me. Where? On desktop, and call it equations.txt. Fine. Okay, and then all of the equations that you have created will be exported unless you click on one and uncheck it. Then that one will not be exported. So you don't need to export all of the equations and dimensions to the file. But for now, I will, and I say link to, and then export. You see already it's exported, so I don't need to export it one more time, and I okay that. Now, if I go on my desktop, you can see there is this text file, equations, and if I open it, all the equations are exported here. And if I just change this number here, right? Let's say I change the length of the shaft, and instead of 4 inches, I make it 6 inches, and I'll save it. And then if I go back here to SolidWorks, all I need to do in order to reflect that update in the text file into SolidWorks, because these two files are linked, I need to do a rebuild or Control B. There we go. Okay, and I mentioned that for you in the lecture, right? Just use a Control B. So a few more items about advanced design, parametric design. So one of them is equation driven curve, and I mentioned this in the past. I do it one more time. So these are basically the curves for which the equation is given either explicitly or implicitly via a parameter, and they are not regular lines, curves, splines, and so on. Okay, so you have really a function to implement, like x sine of x, x sine of x squared, whatever function that is not available in the SolidWorks under sketches. None of these guys. So let's say if I create here a new part and create a new sketch on the front plane, then, as I said, I can create curves for which the function y versus x is given explicitly, or they are given both as a function of parameter t. So the function is expressed parametrically, and then t changes between two limits. So, for example, you can have this function x sine of x squared or x sine of x, right? And let x change between some number to another. So if you go under spline here and use equation driven curve, then you provide the function directly here. So y as a function of x is like x times sine of x, or sine of, let's see if x is squared, if we can say, then x goes between 0 to some number 6, and we get that. And let's see, I guess the x squared term didn't work for some reason. Let me just use x sine of x, and then go from 0 to 6. There we go. Yeah, I have to check it out, but this is a function x sine of x that I did. I can do any other function, tangents, cosine, arctangents, and so on. All of the functions available in SolidWorks, I can do that. Or, as I said, I can do this by specifying a parameter. So if I go here and then go with parametric, and I say x is a function of t, y is a function of t, and then t changes. So here, let's say if I say x is cosine of t plus t sine of t, and then the other one is sine t minus t cosine t. So this is a parametric curve, and then let's say t changes between, if I want to create this 0 to 2 pi, so I just type in pi, and as I said, SolidWorks knows pi. So this curve here is called the involute curve. And what is involute curve? Involute curve is exactly the profile of the tooth of a gear. So if you look at the profile of the tooth of a gear, this curve here, this curve is not a three-point arc, it's not S-spline or anything. This curve is something called an involute curve. And this is one of the few curves that are used for creating the profile of a gear tooth. Okay, so if this is the tooth on a gear, that's this guy. Not all of the profile of the tooth is involute. Only from some point above it is involute. Below that it's not. So above, let's say this circle, it is involute. Below that it can be a simple S-spline or even a line or a curve. What circle is this in a gear? That's the circle I mentioned earlier in this lecture. It's called the base circle. So base circle, for which the diameter or the radius r of base is r of the pit circle times cosine of the pressure angle. Above the base circle, the curve is involute, and for involute, if you have one point here, okay, or a point, if you, let's say, put your origin here, or actually on the base circle here, so this is y and this is x. If you specify any point here by y and x, then you can show that x is and y is those things that I just mentioned, okay? So sine t minus t cosine t. And this is cosine of t plus t sine t. Okay, and when t changes from 0 to another number, then this point starts from origin and then keeps moving on this profile. Now we are not going to use all of the involute profile, we just use a portion of it, and then we get this curve, and then we mirror it, and then we connect with the line, and then we get the tooth profile. Okay, so this curve that you see and I'm creating here for you is an involute curve. And again, we are not going to use all of it if we want to make a gear. Another example, let me just tell you, is a spiral, right? A spiral, if you remember, is like a circle for which the radius is increasing or decreasing as it keeps rotating. So if here, just guess, if I make this cosine of t, x be cosine of t, and y is sine of t, what kind of curve would you get? Just like that. You're right, it's a circle, right? So let's see what happened to the sketch. Let me make another one. So Parametric, right? If I make this cosine of t and make this sine of t, and let t goes from 0 to 2 times pi, right? Yes, you expect the circle with a radius of 1. Now, if, as I'm going inward, I also make the radius shrink, okay? So this radius, I make it shrink as t gets bigger and bigger. Like what? Like, let's say if it accepts exponential of t from me. If it does, that is going to be really good. We'll see. And this one also. So the radius is shrinking as you keep rotating. Then I make this go a little bit further in, so like 6 pi. And then you would get your spiral. Okay, so here you're starting at this point, and as it's what? It's rotating further and further, your radius is shrinking. So you see, it is kind of a spiral. If you make it increasing linearly, then it could again be a spiral, but radius is increasing, not decreasing. So you can make it like this. And then look. Yes, you will get a spiral too. So you can define curves using a parametric method too. Anyways, one more thing that I want to show you is a 3D SP-line. So far, the SP-line that you have seen, and it's useful for creating so many objects, is a 2D SP-line. So you have to do it basically by what? Going to a sketch plane and then clicking on a bunch of points and what? Basically making your SP-line passing through the control points, right? So this is a 2D SP-line. It is in a sketch plane, on a flat plane. What if you want a 3D SP-line? Can you do that as well? And the answer is yes. How? So to do that, you have to go under the Features tab and then go under Curves, and then let's see, it should give you this one, Curves through XYZ points. It gives you this table, and then if you have XYZ points in a text file, you can insert it. Otherwise, you can enter the number. So let's say my first point is at origin, then my next point is at like 5, 6, and -3. Right, and then this point is okay. Enter. Oh, it's not enough. I need more points. So let me create more rows. And then this one is like 1, 1, and 10, right? 3, -3, 0, 6, -8, 9, 0, 2, and 0, and you okay that. Okay, and now you will get this complicated 3D SP-line which is passing through several points. Okay, see clearly that is a 3D SP-line. So you do that by actually, if I made the first point and the last point coincide, it would kind of be like an infinity sign. So anyways, these are advanced tools that you have for 3D designs as well. One other thing I want to mention, which is really good, is Design Table. Design Table is really good for creating libraries of parts and catalogs that basically the parts in it, they all share the same appearance, the same overall features, but the features are different in dimensions, okay? Let's say you want to create a catalog or a folder of different hex bolts, right? So they all look the same, that category of hex bolts, but they are different sizes, or different gears, right? They are all gears, but different moduli, different number of teeth or pressure angles, and so on. So in order to create that, you do not need to create tons of individual SolidWorks files. All you really need is one file and then some parameters, and then you export that to a design table. And then in the design table, I'll show you, design table is something that is linked to your SolidWorks. And then in that design table, if you change anything, your SolidWorks dimensions would change. But more important than that is basically those dimensions that you export, let's say they're all show up in this kind of semi-Excel file. It's not an actual Excel file because the design table Excel file that it is not an external Excel file, is an internal Excel file. So it is saved inside the SolidWorks file. And then if all the default dimensions are under the first row, if you add a second row, and then in the second row you add new dimensions, it's like creating a second configuration of the part. Okay, you get a different part, and each time you can go and activate one of them, right? So I'll show you design table and how to do it. This way you're not, as I said, gonna save tons of files. You only have one file and one semi-Excel file that is saved with the SolidWorks. It's not an external Excel file. And then all you have is several rows in the Excel file. Each row belongs to one configuration of the part. So this way you save a lot of space, and it is way easier to access any of those configurations. So let's see how we can do that, right? So one of the things that is important and useful is if you show all of the feature dimensions on the part first, and I'll show you that, and then go and insert the design table. I make a new part here instead of the previous ones to illustrate it. So I go here, I make it very simple, provide some dimensions, and make some very simple part. Right, and then cut extrude this. So let's say I made this part and I use several dimensions in it, correct? Like 7 dimensions. So now before I move on with creating a design table, as I said, let me first show you all of the dimensions that I used in this part and show it on the part. So I go under the annotation tab of the tree, right click and say what? Show feature dimensions. And when you do that, all of the dimensions that you used will be provided here. Okay, so the depth of this cut 20, 50, 40, 100, 45, and everything, right? So all of these dimensions are now provided. So you exactly know how big this circle is, how deep is the cut, what is the size of the box, what is the depth of the box, and so on. It's good for visualization. Now I go under insert, and then typically you are up here, you don't see tables, but if you scroll down you can see tables, and then you click on insert a design table, then say auto create it for me from this file. As you can see, it is asking you which one of the 7 dimensions do you want to export. So you can hold down Control and select any one that you want, or you can select all of them. So click on the first one, hold down Shift, click on the last one, and select all of them if you want. And then say OK, and as you can see, it will generate for you an embedded Excel file. Okay, so let me bring it back. So where is it gone? It is under the Configuration Manager tab. If you click here and then under Tables, you can see the design table you made. You can right click on it and edit that. And as I said, it is an embedded Excel file. It's not an external Excel file that you can see here. All of those 7 dimensions are exported for the default configuration of the part. Now I can go here and add a second configuration, call it config2 or whatever you want, and then change some of them. So for example, I made the part, I want to make the part taller and thinner. So that 150, I'm gonna change it to maybe 200. The 120, I'm not gonna change. I want to make it thinner, so I make the 50 thickness 30. Then the diameter of the hole, I make it smaller, so I make it 15. And then the offsets, I'm not going to change. And then the depth of the cut, I also make it 30, so that it is basically like a true hole. Okay, so it cuts through the entire object. And I do that, right? So now I have added a second configuration. I can add more and more and more, and each one corresponds to one separate actual part, or one part but different configurations of one part. So here, if I click out, it says you have added a new configuration to the table, and so yeah, I know. And now if you see, not only I have default configuration, I also have what? Configuration 2, but right now it is inactive. If you want it to activate, double click on it. There we go, look at that. Yes, smaller hole, it is true. Then what? The part is taller and thinner. If you want the default, just double click on it. Rebuild. There we go. Okay, so you can activate each one of them. And so you have an embedded Excel file instead of what? Having tons of different SolidWorks files saved. One for this one for this one, and let's say you have 100 configurations. So you're going to have 100 SolidWorks file, but right now you have one SolidWorks file and a design table with 100 rows in it. Okay, so you basically save a lot on the space, and it is easier to manage. So I guess at this point we are done about basics of parametric design. Now I want to talk about SolidWorks options, pack and go, which I mentioned earlier, and the toolbox. I guess the toolbox I mentioned, so there is not a ton. I want to talk about toolbox because, as I said, when you come to SolidWorks, if you click here on the design library, then you have toolbox, and if you click on it and then say add in now, if it's not added in, then it gives you a library or libraries of pre-built files. So this ANSI inch, if you go on it, there are so many different folders. Each folder has specific categories of parts, let's say gears, knots, bearings, and so on. So if you go here, then go under gears category, then there are different types of gears, helical, spur, bevel, and so on. So all you need is, let's say I want a spur gear, right? So I can just hold this, drag it, and drop it here. Then make a read-only file version of it, like that. And believe it or not, creating a gear is absolutely not an easy job to do. At some point we'll probably talk about it, but by no means it is an easy job, okay? Absolutely not easy job. So when you have the option to use something that is pre-made, that makes life extremely convenient for you. Okay, so there we go. That's a part, and I can directly use it as is, right? That saves a lot of my time. Now, what if you want to change it? Let's say I want to add more teeth, or I want to modify this. Can I also modify the parts in the toolbox, or I should just use them as is? No, you can modify them. How? Let me show you. So, by the way, we have a PowerPoint file on Canvas under modules called Sharing SolidWorks Files, Pack and Go and Toolbox, right? Which you go under Canvas modules. You can see it right here after parametric design. Okay, here. So the material I'm covering right now is from the next PowerPoint here, right? This guy. And first, I'm talking about the toolbox. As I said, there are tons of parts pre-built. And now I want to show you if you want to modify them. So it's not really hard. Just right-click on the part and say Create Part to access the configuration component window. So here, let's say I have a Spur gear and I want to modify this. So I right-click on it and say Create Part. And then it gives you this window on the left. And when you have this, then you can modify. So let's say I want to add more teeth. So right now you have 10. But let's say I want more teeth, so I make it like 16. Okay, and since you have not changed the diametral pitch, which is the ratio of the number of teeth to the diameter, when you make the number of teeth go up, the size also go up. Okay, if you make this number bigger, means more teeth per size. So if I make it, instead of 0.5, I make it like 1, right? Then the size goes down while the number of teeth doesn't. Okay, or if I make it smaller than that, then the size goes up without what? Changing the number of teeth. Okay, so as I said, the first parameter that you have to choose is the number of teeth per size, which we call it per diameter, we call it diametral pitch. Then when you change the number of teeth, it will change the size accordingly. So let's say I want 16 teeth, that's fine enough. Pressure angle will just change the size of the base circle. You probably, if you change it, and there are not too many options to choose from. There is just 14.5 and 20 degrees. I would choose 14.5 because, as I mentioned earlier, smaller pressure angle means better performance. And you see also I cannot choose any number of teeth that I want. For small numbers I can, but once you keep going up, it starts jumping a little bit. So right now it is apparently allowing you to go one by one, but in real life, like, it's not easy to find a gear with 197 teeth. And also the diametral pitch, the numbers are not just changing at arbitrary numbers. They have specific numbers that they follow, right? So you don't have some with a diametral pitch of 9 or 7. You have 8, 10, 12. Most of them are even numbers, except for 3 or 3.5, 2.5 that have decimals. Most of them are even numbers. So then you have face width, which is the thickness of this. Let's say I make it 2 units, right? Or even more, 4 units. Right, so you make your gear thicker. Then you have a hub style. Okay, the hub, and if I say I want it on one side, or I want it on both sides, right? Then you will get a hub if you want. If you don't want it, you just say none. Then do you want a keyway? And keyway is effective when you have a hub. So let's say I want a hub. I also want a hub diameter. Let's make it bigger, 8. And then keyway, if it allows me to choose a square, I need a whole size here. Let me see if I can find that. Overall length, make it bigger. Okay, so this is the shaft on which the part is rotating. You can have a hub or not. And then you have nominal shaft diameter. So let's say 1, but it's too small. Let me get rid of the hub so that you can see the shaft hole. So let's say I don't want any hub, I just want the shaft. And nominal shaft diameter, let's choose a big number here. 8 should be good to go. Then I need a keyway. Let's say square is good. Then I OK that. And it should give me this nice gear with all the specs that I have provided. Okay, so you can configure all of those parts by right-clicking and say create part. Okay, so take advantage of this.